Hello friends, I welcome you all to this session on PowerPoint engineering. So in the previous lecture, we solved one problem which is related to reheat Rankine cycle, and this was the problem which I solved. And now what I have done is I have increased two more state points. So this was 6 and this is 7 and this is 8. And in these points I have evaluated the temperature, as these are saturation, these temperature at these point the temperature will be saturation temperature corresponding to this pressure. So these will remain the same, and here the entropy will be entropy of saturated liquid, and here it is saturated vapor. So this I have evaluated. Now apart from this, what I have done is I have also drawn the TS diagram for this particular problem, and let me show this to you that how this TS diagram changes as I increase the reheat pressure. So at this point the reheat pressure is exactly same as that of the boiler pressure. So you can see there is nothing new to it, because as the reheat pressure becomes same as the boiler pressure, so you can say that there is no reheat applied at all. Okay, so that's why you are only able to see this line. Now what I'll do is I'll change this reheat pressure, I'll reduce this reheat pressure. Now see the impact of this reheat pressure on the efficiency as well as the work output, and look here what happens. As I increase the decrease the reheat pressure from 150 to 140 bar, then the let me go to, now it is 1072 and the efficiency was 35.5. Now if I move to 140, so it becomes 1090 and efficiency slightly improves. And here also you can notice that there is a slight amount of reheat given, very small, which is even not possible for you to view it from here. So if I increase it slightly, so you can see there is a slight improvement. Okay, now what I'll do is I'll reduce this reheat pressure more from 140 to 130. Now you can see there is again some amount of reheating is happening, and again you can see there is slight improvement in the efficiency, slight. Now I increase it from and also you can see that this particular line is going away. Now if you notice this and this work and efficiency I'll discuss later, but you just notice how this thing comes into picture with reducing reheat and how this line moves to right, resulting in improvement in the dryness fraction. So from 130 to 120 if I go, so it has again moved, and now you can see a substantive, little bit, not substantive but little bit amount of reheat from 120 to 110. Now again improvement, and this is now coming into picture. So from 110 to 100, then to 90 bar, then I move to 80 bar, then from 80 bar I'll move to 70 bar, from 70 bar it is 60 bar. So as I reduce the reheat pressure, you can now see very clearly the reheat value, and at the same time you can also see that this line has moved toward right, this one expansion line, and resulting in what? Resulting in what we say better dryness fraction at the exit of the turbine, this one. So if I increase it further to 50 bar, now again from 50, so if I move to let's say 30 bar, so it is moving out now, and there is no point in drawing this like this, because that is not a very good option, because we have to now move to up, because this is now in superheated region. So I have to follow the pressure line, which I have not drawn here. So now you can visualize what is happening as I reduce the reheat pressure. And let us also do it with certain different approach. Here what I have done is same reheat pressure I have written in decreasing order from 150 bar to 6 bar, and then I have evaluated the ratio reheat pressure to the boiler pressure. So so that is varying from 1 to 0.04, and then I have evaluated the efficiency. So what I have done is here I have changed the pressure, I have noted the efficiency, and I have written it here, and at the same time I have also noted the dryness fraction here, and this also I have noted. So this I have done for from 150 bar till 6 bar, this one. Then I evaluated the improvement in the efficiency uh, of this particular cycle if I reduce the reheat pressure. So how this has been done? So this is nothing but the difference between the actual obtained and that when the reheat pressure was exactly 15000, and then divided by this value, and that is what I have obtained. So now if I plot the this as x-axis and try to observe what happens here, then you will be amazed to see a very different thing. So what I have to do here is I have to just change the axis of this uh, format data series secondary axis. Now that is what you will be able to what where it is. It should not. Okay. Now this is the one. Okay. Now that is what you should be seeing. Okay. Now if you look this particular curve closely, though I have lesser number of data point, I could have taken more, but if you just observe what is happening here, so where is the axis? Yeah, this is the axis. So now if you look that for this ratio, pressure ratio, let us also give legends, not legend, access title. So this particular value is nothing but it is P reheat divided by P1. This particular axis is telling you about the change in efficiency, the delta eta, and this particular one is telling you about the dryness fraction. Now if you again, I have to do one more thing. I have to increase the font a bit so that it can be visible more. Now it is okay. Now you look what is happening to efficiency as I reduce the reheat pressure. So with reheat pressure reduction, I am continuously gaining the efficiency. So efficiency is continuously increasing. Look, it is continuously increasing and it is attaining a maximum value close to 0.2. And then if I reduce the reheat pressure further, then it reduces. That means the efficiency improvement is not there. In fact, efficiency decrement is there. Okay, so you can also see it from here. Around 0.2, it is attaining a maximum value, and 0.2 to 0.25 I can say, and then it starts reducing. So efficiency reduces. And what about dryness fraction? Dryness fraction improves continuously. So if you look at from 1, so it is, let us also do what? Let us keep it at 1. Okay. So when there is no reheat, that means reheat pressure is exactly same as boiler pressure, it is 0.86. And as I reduce the reheat pressure, the dryness fraction continuously increases. And after say about 0.2, there is no point of what we can say, dryness fraction remains more or less the same. It doesn't change. Why? Because after this point you can see it has moved to the superheated region and there is no point of talking of dryness fraction in this particular region. So what is the takeaway from here? The takeaway is that the reheat pressure should not be less than or it's for optimum value. So if you want the maximum efficiency from a power plant, then the reheat pressure should not be more than 0.2 to 0.25 times the boiler pressure. So this is what I have demonstrated with this particular exercise. So this is a general practice also. So remember, the optimum reheat pressure for most of the modern power plant is ranging from what? Is ranging from 0.2 to 0.25. Remember this. Okay. So that is what you have gained from this particular exercise. And if you look any standard textbook, there you will be able to see these types of charts, but you must be wondering there from where these charts have come. So now I have shown you that how to draw these types of charts and how to understand what these charts are telling you. So in this chapter, till this point only. In the next chapter, I will be in the next lecture basically, I will be telling you about the regenerative feed water heating, because from here you cannot get a major efficiency boost. So what you have to do is you have to internally rearrange the energy, and that is done with the help of regenerative feed water heating. So thank you very much for watching this particular lecture. Take care.